Hi, my name is Patrick, and I will be going over how to create a one hot state machine and a reduced state machine in CircuitSim. So to start off with, I have the DFA for my state machine right here. I have S0, S1, S2, S3, which are my states, and I also have an obligatory start state, since this will be a one hot state machine. What makes the one hot state machine different is that each of the bits encodes a separate state. So if we are in the 0th state, then we will have the 0th bit on. If we're in the first state, we will have the first bit on. Second bit. Third bit. So let's just write that down. Wow, I wrote that down so fast. Okay, so I think you get the idea. Each of the bits represents a single state, but how does that look in the register? In this case, since we have 4 states, we will have 4 different bits in the register to store each of the states. If the 0th bit is on, then we're in the 0 state. So in the register, that would be 0001 because the 0th bit is on and all the other bits are off to signify that we are not in like the first state or the second state. We are in the 0th state. Etc., etc. for the rest of the states. So if we are in the first state, then the first bit is on, like so. Again, 0th bit, second bit, and third bit are all off to signify we are not in those states. So if we're in the second state, then the sequence is 0, 1, 0, 0, and the third state, 1, 0, 0, 0. So those are the values that we're going to store in the register when we're in each of the states. Now you might ask, what happens when we have a state that isn't listed here? Like what happens if the register has a value of say 1001 or 1111? What happens to the state machine then? So in our state machine, these values are basically undefined. We should never be able to reach them by going through all the transitions. So we don't really have to worry about them. There's also one last state I'm forgetting about, and that is the start state. So when you first initialize a register, all the values in the register should be 0, like this. That is what the start state is. It's essentially the uninitialized register where you don't have none of the bits are on, so you don't know which state you're in. Start state really isn't that important because once you exit the start state, you will enter the state machine. You'll enter S0. And at that point, you will never be able to go back to the start state because it is only there because the register is uninitialized when you start out the state machine. To go from the start state to the 0 state, what you have to do is you have to set up essentially a bunch of AND gates that will detect when the register is all 0, and when it's all 0, then immediately go into the start state, or state 0. I'll go a little bit more into what that entails later on. What we usually call this is the kickstart, because it's kind of like kickstarting the car. You're kickstarting the state machine, and after you kickstart it, it will be running. Alright, so let's actually start making the state machine. Let's start up CircuitSim real quick. And first, let's load up the template file. I made a copy of it, so don't worry about that. But just make sure that you use the template file. If you don't use the template file, then there's a decent chance that something's going to screw up the tester, and that would be really annoying all around. Alright, so first thing we want to do is get our register. As I stated earlier, since each of the bits encodes a separate state, and we have 4 different states, that means we need 4 bits in our register, which is also why each of these states is represented by a 4-bit number. So let's make a 4-bit register. Just go to memory, drop down the register, and change the bit size. Alright, so now I have the register. And since each of the bits in the register encodes a different state, I'm going to want to access each of the bits so that I can know if I'm in state 0 or state 1. So let's just set up a splitter. I'm just going to make it face the top because that looks better. Bit size should be 4 and fan out should be 4 because we have 4 bits in a register and we're accessing each of the bits. Assign all the bits to the correct fan out, and now we should be good. I'm also going to set up some tunnels so that it's easier to know like which state I'm in right now. Just a heads up. So the way the splitter is set up, the 0th bit in the register is at this 0 fan out, and that means that this line will be 0 when we are not in state 0, and it will be 1 when we are in state 0. So that applies to the rest. So 1, 2, 3. If any of these lines are on, then that means that we are in that corresponding state. So let's drop down a couple of tunnels. All right, and connect them up. So as I mentioned earlier, 0th bit represents state 0, first bit represents state 1, second bit represents state 2, and third bit represents state 3. So now let's set up each of the transitions. Oh wait, I also forgot. I should probably explain what all these inputs are. So on the state machine, we have a couple different inputs. We have G, which is like essentially a button that you press that will change which state you go to. So if I'm in state 0 and I'm holding G and I toggle the clock, then I should not go down this transition. I should stay in state 0 because there's a transition from state 0 to state 0 if G is held. If I'm in state 0 and G is not held, then it should go to state 1 if the clock is toggled. Also, you probably learned this in class, but the register's value changes on the rising edge of the clock. So when the clock goes from 0 to 1, that is the time when whatever value is on this data line will be stored into the register. I won't really go over that because you should already know that. Reset's just what you attach to the reset line on the register so that you can just reset the value to 0. And I didn't actually assign outputs to my state machine. I'm just going to say that 0 state will turn on A, and first state will turn on B, etc., etc. Alright, so now I have my outputs. I know how each of the states encoded. Let's start making transitions. So if I'm in state 0, and G is held, then I should go to S0 as my next state. So how I'm going to structure this is I'm going to go to a state, see all the arrows that, or all the transitions that go to that state, and then make a set of gates for each of the transitions. So I have a transition that goes from S0 to S0, and I'm currently working on transitions that go to S0. So I have S0 for the current state, and I have G for G will be held. So if I'm in S0 and G is held, then I should go to S0. And the next transition that goes into S0 is the transition from S2 to S0. So if I'm in S2 and G is not held, then I go to S0. So I said that if G is not held, which corresponds with a NOT gate, which I can just add onto my AND gate right here, because if you didn't know, you can just negate one of the inputs on the AND gate. I'm going to be negating the right input. So negation is represented by the little dot. So this represents the transition from S0 to S0 when G is held. And this represents the transition from S2 to S0 when G is not held. Now, if either of these are on, then I will go to S0 as my next state. So that can just be represented with an OR gate. Because if either of these are on, then we go to S0. I also probably forgot about one of the most important transitions. So actually, the number of arrows pointing to S0 is 4, because you have this transition from S0 to S0, this transition from S2 to S0, and start to S0 is kind of like 2 arrows, because if you are in start and have G held, then you'll go to S0. If you're in start and you don't have G held, you also want to go to S0. So you want to go to S0 from start, no matter what. So let's just make that real quick. So as I said earlier, you know that you're in start if none of the register bits are on, because that means that you have no actual state right now. So we can do that by just doing a simple AND gate check. If all of these are 0, then we will go to the kickstart. I'm going to use a 4 input AND gate for this, because we have 4 different states, and I'm NOTing all of them because if S0 is 0, S1 is 0, etc., then I want this AND gate to turn on. So that only happens if I NOT all of them first. Alright, so now my kickstart, and I'll just add that over to my other transitions going to S0. Great. So now we can see that this kind of works, because if I'm in state 0, or not state 0, if I'm in the start state because this register is storing 0, then next state should be 0. But now we have to actually configure how the register knows which state to go to next. So there's no input feeding into the data inline over here, which means that if I toggle the clock, then nothing's going to happen. I should also just set up all these lines over here. So clock input should be connected to the clock input on the register. Clock is just, it's like the clock in any kind of microprocessor. As you heard in class, when the clock goes from 0 to 1, rising edge of the clock, that is when values are stored into the register. The clear is going to be connected to the reset, because I'm going to want to clear the value of the register when reset is held. Alright, and the enable should always be on, because there should never be a scenario when enable is off. Register should always be working. Okay, great. So basically this input, this data in, should look like the exact mirror of this side over here. It's going to be a fan out with 4 bits, and each of the bits, or sorry, it's going to be 4 fan out, each of the fan outs is 1 bit, and each of those bits corresponds to a next state, or the next state that the register should hold. So let's do a quick copy paste there. And I'm going to want a similar set of tunnels I have on this side. I'll use N to represent next state. So I'm just going to label this top one N0 because it's connected to the 0th bit, and N1 for the next one, N2, and N3. Okay, so N0 is going to be 1 if we want the next state in the register to be 1. Sorry, N0 is going to be 1 if we want the next state to be state 0. And 1 is going to be 1 if we want the next state to be 1, etc. Only one of these should be on at any one time. So if N0 is on and N1 is on at the same time, then you know you have a problem. Because as I said earlier, the only valid states in this state machine are when only one of the bits is on at a time. So if you have more than one bit on, then that's just an issue, and you should not have that. So I'm just gonna cut the video here and start setting up the transitions for S1, S2, and S3, because I think you probably have the idea. Alright, so I'm back, and I just did all the transitions that go to S1, S2, and S3. So now this state machine should work fully, but we still have to wire up the outputs. The outputs that I stated earlier are kind of trivial to implement, so let's just make it a little more interesting. State 0, we will have outputs A, B, and on state 2, we'll have outputs C, D. So basically what we have to do is we have to set up an OR gate for every single one of these outputs. So an OR gate for A, OR gate for B, C, and D. And with that OR gate, I will feed in all of the states that could lead to that output. So if I have A, looks like A is only reachable from state 0, so let's not worry about that yet. So B is reachable from 0 and 1, and D is reachable from 2 and 3. So let's set that up. I'll just take this tunnel down here. Oops, that's annoying. Let's take this tunnel and add the outputs over here. So I will feed into C I'll feed into B states 0 and 1. Alright, so now B should be lit when we're in state 0 or state 1. Next I'll set up D. And D should be on when we're in states 2 and 3. Alright, so that goes for all the outputs with more than one state. Now I'm just going to set up A and B, or set up output A and C, because both those outputs, there's only one state that corresponds to them. So A is only dependent on 0. So I'll just wire that up directly. And C is only dependent on 2. Alright. So that should be good for all the outputs. Now let's just go through and test our state machines because this should now be done. Alright, now I'm going to test to see if the transition from start to S0 works. So right now I'm in start because the register has a value of 0 and that corresponds with the start state. Going from the start state to S0 should happen if G is held or G is not held. So let's test that out. G is not held, and I can indeed go from start to S0. Let's reset that, and now does the same transition work when G is held? It does. Okay, so now I know that my transition from start to S0 works. So I'm just going to toggle through all the transitions. Let's first go from S0 to itself when G is held. Okay, that's good. We're still in state 0. Now let's go to S1 when G is not held. And that looks like it also worked. Next, I'm going to go from S1 to S3 when G is held. And that also works. Let's try go back to S1 when G is not held. And it looks like that transition works as well. Now let's go down this transition from S1 to S2 when G is not held. And that's good too. Next I'm going to see if toggling the clock and holding G will keep me in state 2. It does. And let's go back from state 2 to state 0. And G should not be held. So that looks like it works too. I think I tested every single transition except for the transition from S3 to S2, so let's test that. I'm just going to manually input state 3 into the register, and that transition works. So now I've tested every single transition in the state machine. I wasn't really paying attention to the outputs, so let's take a look at that too. If I'm in state 0, if I'm in state 0, then and we are on, that's good. Let's move on to state 1. That also looks good. In state 1, I'm outputting B. Let's go to state 2. And state 2, C and D are on, which corresponds to what I said earlier. That's good. And let's finally go to state 3. And that's good too. So looks like all the transitions in my state machine work, all the outputs in my state machine work. Did I test a reset? I can't remember. Let's test that. Yeah, so reset works too. Resets the state machine to 0. So that should be it for making this one hot state machine. Hope that you found that useful. Also, just a heads up, the value shown here in the register, that's the hex value. So when I was in state 0, that was equivalent to 0001 over here, which is 1 in hex. So these are all hex numbers. This would be 2, this would be 4, and this would be 8. Yeah, so that's about it. Thanks for watching. Okay, so there's just a couple things you should do before turning in your reduced state machine, one hot state machine. First of all, this isn't the test file I was working on earlier. This is the actual file that we give you with a little bit more components put in. So first of all, right here where it says your name here, put your name. It should be pretty self-explanatory. You just type into the box and it changes your name. I'll do that to my reduced state machine too. Okay, that looks good. Also make sure that your register is named reg, R-E-G, no spaces, no quote marks, just reg, like that. If you don't label your register properly, it's gonna completely blow up the tester, and you probably don't want that. So name your register correctly on your one hot state machine and your reduced state machine. And that should be about it in terms of labeling. Now let's go over the turn-in procedure. So this might be slightly different than what you're used to. So my file is here. I'm just going to go to Gradescope. Already have a window set up for that. And I'm just gonna turn this in. You just click on the site. You've probably already done this, but yeah, you click on the course, click on this homework, it's homework 4, drag and drop the file, and hit upload. Now, if it says it's been submitted successfully, then you're all good. But if you wait a little bit, the autograder will run and eventually the results will pop up in this window. So let's just wait for that to happen. It's probably going to take a while, but don't worry about that. Alright, well that took kind of a while, but now you can see a bunch of grader output that tells you if your transitions work properly. Yeah, so this is just a list of like every single test that was run. Since none of the tests failed, well, the score is 100, so it's all good. You don't really need to worry about this debug output. That's more useful if the tester fails and you have to get one of the TAs to fix that out for you. And it looks like that's good. So yeah, I passed all tests. Actually, let's look at what happens when you fail a test. Let's see what that looks like. I'm just going to delete one of the some of the transitions over here. And in the reduced state machine, I am going to rename this register just to show you what happens when your register is wrong name. Save this file, and let's submit that again. Okay, so all we have to do to resubmit this file is to click the resubmit button, bottom right corner, and then you can either drag or drop or select your fsm.sim file, click upload, just like the submission process. And once again, you're gonna have to wait for the autograder to finish. Alright, so that finished. You see, I have now failed a bunch of tests. I failed most of the RST grader.tests because, well, we can check. Let's scroll down. The error message is given right here. Register reg does not exist in the circuit, and that's because I renamed my register from reg to something else. So couldn't find the register and couldn't run the autograder. And you can see I also failed one of the one-hot grader tests. And it tells you exactly what happened. This transition from state, 0, 1, 2, 3, for transition from state 3 and not G did not work as expected, returned the wrong value, and that's because I deleted that transition. So using the tester, you can find out which transition you're failing and hopefully fix that. And that's about it.